So I've got a typical 18-inch subwoofer driver made by B&C Speakers mounted in a wall in our warehouse, and the backside just opens up into the next room. So it's as close as we can get to an infinite baffle situation where we can isolate and measure just what the driver does in essentially free air, where there's no resonances or damping from an enclosure. You see, I've done several polls on social media asking basic questions of the audio community about how subwoofers work, how microphones work, what the phase graph means, stuff that audio people should know, right? Tens of thousands of you responded, and the results were all over the place, often split 50-50 on simple yes or no questions. I see people trying to compare their test microphone output to the main output from their console, and their system never seems to be in phase, and they don't know why. So today I'm going to simplify the most counterintuitive aspects of the phase graph. The amazing team over at B&C Speakers sent me an expensive, super fancy scientific laser measurer so we could get the most accurate reading possible of the driver's physical movement over time and compare that against a few of the data points, like a test microphone, a voltage reading, which is just a pair of resistors connected to the driver in parallel, and an active non-contact current reader placed on the positive line going to the speaker. I ran the wire through it a bunch of times to increase the gain and overall clarity of the reading. All of the outputs from these devices have been converted into their voltage equivalents if they weren't so already, and will go into the Yamaha Rio 16 digital stage box preamps, and then run over Dante to the computer into Logic, where we can do some basic processing like delay compensation, and then pipe everything over to Signal Scope for analysis. I took a lot of time selecting these sensors and microphones, trying out many different units because some had hidden high-pass filters and phase reversals, odd latency issues. It was a nightmare. For example, before we use the Yamaha Rio, we need to be aware that Pro Audio analog inputs and outputs usually block DC voltages from passing through them, and this applies to amplifier outputs as well. This is known as AC coupling, and for example, if I take a battery and touch it to the terminals of the mic preamp and look at it on an oscilloscope, there's a spike on the oscilloscope, but it quickly goes back down to zero when it should just stay positive the whole time. If I release the battery, there's a negative spike, but it again goes back to zero. It should have just gone from positive back down to zero. So this is the effect that AC coupling can have on oscilloscope readings. If we consider the laser measurer and we touch the battery to the speaker and make it go out and stay out, we see the same thing. Releasing the battery, same thing. Because this essentially acts as a high-pass filter, it introduces some amount of phase shift into the signal. In particular, high-pass filters add positive shift to lower frequencies. We can demonstrate this very easily by taking an EQ in Logic and applying a high-pass filter and looking at what it does to the magnitude and phase. We see positive shift in the low frequencies associated with the tuning frequency and the steepness of the filter. As I already pointed out in another video, it's important to understand what the phase graph is telling us here. It could be telling us when in time the sound is happening to account for a literal time shift somewhere in the signal path. For example, maybe the low frequencies are arriving earlier or later than everything else. Or it could be telling us that there is an alteration in the formation of the wave, even though it technically happens at the same time as everything else. Also, phase shift to the right on the oscilloscope corresponds with negative or downward shift on the FFT phase graph, which corresponds with either lateness in arrival time or a delay in the wave formation compared to the reference. So in this particular case, the EQ isn't causing the low frequencies to happen earlier than everything else, but it is reshaping the waveform to cause a phase shift. You can check out that other video for fuller explanation of the topic. It's a bit confusing for sure. Maybe check it out after we finish the demonstration in this video. The point is, if I run out of the Rio and back into it a bunch of times, you can see the high-pass filter really starting to stack up and even cause phase shifts up in the subwoofer frequency ranges. How do I analyze the low-frequency phase of something if all of my measurement tools themselves introduce phase shift? Well, I have with me a specialized kind of audio interface that doesn't block DC voltages. This is known as DC coupling, and these are normally used by people doing synthesizer work where DC signals control certain things about the devices that are making the AC sound waves down the same audio lines. You can see that when I touch the battery to it, the oscilloscope reading is more what we would expect. And when I press in on the driver, we can see the laser reading reflect the actual position of the driver at all times. If I run out of this unit and back into itself, we can see that there's no magnitude or phase shift of any kind. Digital signals don't add any phase shift either, so if I go Dante all the way from the computer to this amplifier, I can come out of the amplifier and measure the voltage output by going back into this device, which has no high-pass filter or phase shift, and see what the amp itself is doing. Okay, so it looks like the amp is flat all the way down to about 5 hertz, where there's some kind of high-pass filter, which I'm sure is there to protect the amplifier from sending DC voltages to speakers. Now, I want to use the Rio as my I/O device for testing because it's a way higher quality unit overall, and even though the preamps add some amount of shift to the signal, that shift is identical on each channel. So as long as I am doing comparative analysis between data inputs, the shift won't matter because we'll be looking for differences between the data, not the absolute values of the data. Also, what I'm going to do is use the voltage output from the amp as the reference trace against which to compare all of the other incoming data. Instead of using the original input signal to the amp, I figure overall the amp is really flat anyway, and since it is the amplifier that is driving the speaker, anything we measure that is the downstream result of the speaker's actual behavior already has the little bit of shift from the amp taken into account. And just like the Rio inputs, all incoming data will have this shift equally baked in, so we don't have to worry about it as long as we're doing comparative analysis. First, let's check to see if everything is working and is in polarity. I have a pre-recorded sound that's just a burst of positive voltage. So if we play it, we can see that it makes the driver move outward just like the battery did, but then immediately return to a nominal position. Here's our voltage reading and our current reading. And here's the laser. And here's the microphone, all showing a positive initial spike in the signal, which means our polarity is correct all around. In fact, we can confirm the mic polarity by producing a positive air pressure burst just by using my mouth. Kids, don't try this at home. You can see the initial spike is positive, and of course there's a ton of disturbances after that, but then here, I'll reverse it and make a suction. This is because most condenser mics are designed to output a positive voltage when positive pressure moves the diaphragm backwards toward the back plate, and the voltage output is proportional to that distance at all times, and the reverse is true in the other direction. If we disconnect the speaker from the amp and close the voice coil circuit and then just tap on the driver, we see that it produces a negative voltage spike, and you can also see this on the laser. Now, in this case, the current will actually be polarity flipped because we're the ones physically moving the driver's voice coil, not the other way around when it is being driven by an amp. This becomes important really soon. As far as time aligning the measurements, the voltage, current, and microphone are all analog, so there's no delay inherent to these signals. The laser has a round-trip processing time of 0.31 milliseconds, and at our audio sample rate of 48K, this is about 15 samples, so we'll add that to all of the other signals to account for this. Furthermore, the microphone capsule is about 1 inch away from the dust cap, and 1 inch of travel time for sound is just over 3.5 samples, so we'll round up to 4 and bring down the delay on the microphone to 11 samples. I hope that made sense to everybody. Now let's collect the data. First, let's take an impedance measurement of the speaker. Impedance is how much the speaker resists the flow of electricity through it. Lower numbers mean electricity flows freely, and higher numbers mean it resists. With coils of wire moving through a magnetic field, the resistance changes per frequency. So let's run a sine wave sweep and see how it responds. We can see an impedance spike around 30 hertz, but overall the level kind of sits around 8 ohms until it gets above about 200 hertz and then skyrockets. If we think about it, the driver's velocity as it moves back and forth is going to be the greatest at the physical resonance frequency, where the driver naturally wants to move the most given some input energy to the system. Maybe we just throw a rock and hit the driver, and it will want to jiggle back and forth a little bit afterward at some frequency. That's the resonance frequency. And so with equal input strength at all frequencies, the driver will move the most efficiently at the resonance frequency. But so, considering that when we pushed on the driver to make it move instead of the driver being moved by the power from the amplifier, the moving coil produced an inverse polarity current of its own in relation to the power from the amplifier. And this would impede the power coming from the amplifier when the speaker is connected to it. to it. The greatest natural amount of this impedance will happen at the physical resonance frequency of the driver, where it would naturally want to move on its own most efficiently apart from the amp. So at 30 Hz, there's going to be the most polarity inverted electrical pushback to the amp when it is being driven by the amp, because of the driver's propensity to jiggle on its own the most at that frequency. These two things kind of fight each other in the balance. If the speaker's QTS parameter is way less than 0.707, we should expect in theory to see a very smooth physical response from the speaker throughout this frequency range when driven by an amp. Values higher than this would potentially yield an acoustic bump in the frequency response of the driver around the resonance point. The higher frequencies experience increased resistance for reasons that I won't go into this video, because we're mostly concerned with the subwoofer frequency range. Next, I'm going to run pink noise through the speaker. On the FFT graph, the amp's voltage reading is set to be the reference input. And again, we're using a transfer function so that everything is being compared to the reference, and we're just looking for the differences in any new data. So let's take a look at the current reading. We can see that it starts out with nearly 0 degrees of phase shift at 1 Hertz, but gradually approaches almost negative 60 degrees of shift around 10 to 20 Hertz, where it sharply flips to positive 60 degrees of shift by 40 Hertz. It looks like it crossed 0 just under 30 Hertz, and then slowly shifts back to negative 60 Hertz by 1 kilohertz or so, where it basically stays for the rest of the way up. It's interesting how the magnitude response is basically a gradual decline starting around 150 Hertz, but with a dip associated with the 30 Hertz area, which is the same frequency that experienced a momentarily sharp phase shift into the positive region, and it's also the same frequency that showed a strong increase in electrical resistance. Let's take a screenshot of this response and then run some sine waves and look at the oscilloscope and compare the two. Here's 20 Hertz, and the black trace is our voltage reference, and the green is the current reading. You can see that the current is behind the voltage. There's 30 Hertz, and you can see that they're right together. At 40 Hertz, we're now ahead of the voltage. And at 150 Hertz, we're back together. Up at 500 Hertz, we're behind again. Let's zoom in so we can see that. So the first thing I would wonder is if these electrical responses will show up at all in the physical and acoustical responses of the speaker itself. So here with pink noise is the laser measurement. Okay, interesting. So we can see that the magnitudinal response is basically just a smooth nosedive down from 1 Hertz upward. It's also interesting how the phase basically nosedives from 0 as well, approaching negative 180 degrees of phase shift by about 200 Hertz, and then basically staying around there up past 1 kilohertz or so. We don't see any indication of anything different happening around 30 Hertz like we saw in the electrical readings. So it's likely that this driver has a QTS of way less than 0.707. In fact, probably around 0.3 or so, which means the electrical and physical forces are well balanced. All right, and finally, the microphone measurement. Very strange. So it basically looks like a polarity inverted copy of the laser reading up to at least 400 Hertz or so. I actually double-checked my initial polarity tests and swapped out the mic for a few other RTA mics I had around the shop to make sure this wasn't a mistake. The reading is correct. We can actually switch the reading here so that the laser is the reference trace. So yeah, it's basically shifted up by 180 degrees, and at super low frequencies, it seems like there's some positive phase shift relative to the rest of the signal, probably because of the mic's own high-pass filter that the laser just doesn't have. And at higher frequencies, I think we're starting to see discrepancies and disturbances from the fact that we've got the mic so close to the driver, and these wavelengths are shorter than the size of the cone. So maybe the sound starts to be a combination of individual sources like the dust cap and the outer edge of the surround and stuff, and those are all different distances away from the microphone capsule. I'm going to introduce a phase reversal to the microphone input and just see what that looks like. Okay, interesting. It tracks pretty well with the laser around here at least. So I imagine that this could all be very confusing because you could have a main out from your console or the power output to the speaker that is here on the phase graph. The speaker could be moving here on the phase graph, and then your microphone is reading here on the phase graph. Or maybe the original signal is here on the phase graph while the speaker is here and the mic is here. I feel like I just want to see some slow motion footage of all of this happening to actually confirm what is happening and when. Let's think about the driver. So, the first question we should ask is, what does it mean when something moves up or down on the phase graph? Does a negative phase shift on the graph mean that it is moving forward or backward in time relative to the reference, or something else entirely? For example, when the phase response of the driver's physical movement, as measured by the laser, starts near zero but then nosedives down to negative 180 degrees, what is actually happening in reality? I devised a simple test to be able to confirm what's going on here. I figured if we pick a few different frequencies and take slow motion footage, we can also have something else in the shot which represents the reference signal going into the speaker, such as LED lights that flash green with positive voltage swings and red with negative voltage swings. We can see when the driver actually moves in accordance with the amplifier signal going into it, since we know that LED lights flash right in time with the electrical signals. Side note, since LEDs actually operate on a combination of voltage and current, and so a phase shift between the voltage and current could result in some strange LED behavior, I'll just pick 3 frequency ranges where the voltage and current had 0 phase shift. So that's 1 Hz, 30 Hz, and 200 Hz. 3 frequencies should be enough to get a general sense of what's happening. With each test, I'm going to start the camera and then turn on the sine wave generator, which always begins with the positive half cycle of the waveform, starting from the 0 crossing, as we can see here on the oscilloscope. Here's 1 Hertz, with the camera at a normal frame rate since it's already slow enough to observe. Here's 30 Hertz, but at 1,000 frames per second. And here's 200 Hertz, also at 1,000 frames per second. But I'm going to time stretch these footages so they all appear to happen at the same speed from a frequency standpoint, and align them using the first green flash of the LED. We can see that the 1 Hertz footage shows the driver moving nearly right in time with the LED flashes. And this corresponds to about 0 degrees of phase shift we see on the laser response graph. At 30 Hertz, we can see that the driver doesn't seem to move immediately or something. It's like it takes a little bit of time and is almost delayed a bit. So it's like maybe a quarter of a cycle behind, which corresponds to negative 90 degrees of shift we see on the phase graph. And then by 200 Hertz, it basically looks like it takes an entire half cycle before the driver really seems to move significantly. And by then, it's a half cycle behind, which corresponds to negative 180 degrees of shift we see on the graph. So basically, as things get more negative on the graph, we could maybe say that they're happening later and later in time, but it's not actually that simple. Of course, nothing ever is, right? First, as frequencies get higher and higher, their wavelengths get shorter and shorter. So a negative 180 degree shift at 200 Hertz is going to be a lot later in actual time than negative 180 degrees of phase shift at 1 kilohertz. So there's that. But also, we can see that the driver does actually start to move at least some amount when the first LED flashes. But it is very, very small and takes time to essentially build up to the full swings. So what's really going on here? For this, we need to look at the oscilloscope readings at these frequencies. Again, here's 1 Hertz, and we can see that the laser and voltage readings are in phase. At 30 Hertz, if we look at the beginning of the sound, it looks like the laser reading wants to begin around the same time as the voltage, but it's a tiny bit late, and the waveform lags to end up being a quarter wavelength behind by the time it gets fully formed. At 200 Hertz, again, we can see that the driver does want to start moving a little bit immediately when the signal hits it, but the waveform, again, lags so much that by the time it builds up to a steady state after a cycle or two, it's a half cycle behind. And my guess here is that the physical weight of the driver and the stiffness of the surround come together in various ways to produce a kind of resistance to movement that is just enough to cause the driver to essentially lag behind in its ability to fully form an oscillating wave at higher and higher frequencies. It doesn't seem to be a set amount of time. Otherwise, we'd see a continued downward phase response on the graph with higher frequencies, but it levels out at around the minus 180 degree mark or so. Basically, above 200 Hertz, frequencies are going to be about a half cycle behind in their full steady state formation. And by the way, this is also true if we take the driver off the wall and just have it laying on the table or hanging up in the air. And I also tested this with some other different sizes of drivers, and they all do the same thing. This does follow the general mathematical principles for simple resonating objects, and perhaps we should dive into those in another video. The microphone reading is the most interesting to me, though, because it is consistently about 180 degrees out of phase with the driver's movement. We know the polarity is correct, where a positive air pressure produces a positive voltage output to the preamp. After talking with several super smart people at major R&D departments like B&C and Nexo for a while, this seems to have to do with the fact that pressure sensing is actually a derivative of the physical movement of the driver. In fact, it's a second derivative. When the driver moves, we can make a graph of its position in space at any point in time. We'll call this displacement. Let's say that the driver is at rest and then starts to move outward. The velocity of the driver would look like this. The acceleration of the driver, which is the change in velocity, would basically just be a spike here and then a dip here. Make sense? Maybe some of you need to go pull out your notes from high school physics. If we switch gears and look at a sinusoidal displacement, which is what drivers do when they're making sound at some particular frequency, moving smoothly in and out, where is the velocity going to be the highest? Well, it's going to be the highest right here when the driver is moving through the midpoint of its travel. Where is the velocity going to be 0? It'll be 0 when the driver's way out at the extremes, about to change direction. And then where will the velocity be the least? Right here. Remember, we shouldn't usually use the term speed when talking about how fast the driver is moving here, because speed is just an absolute value, but velocity has direction accounted for, and so it can be positive or negative, which is what we need to think about. If we complete the graph for velocity, we can see that basically the whole thing has been shifted by 90 degrees to the left, a quarter cycle at this frequency. So velocity as a derivative of displacement produces a positive 90-degree phase shift. If we think about the acceleration of the driver, when is it accelerating the most? Well, it would be when there is the greatest amount of change in velocity, which is right through here when the velocity is increasing the most. Where is the acceleration 0? It's going to be when the velocity is holding steady, which is here and here. And then where do we have the most deceleration? Here, when the velocity is decreasing most rapidly. So if we complete this graph, we can see that since acceleration is the derivative of velocity, it produces another 90-degree phase shift. Acceleration is therefore the second derivative of displacement and has a positive 180-degree phase relationship to it. So then let's say that the driver was originally at rest and then begins to move sinusoidally. What would we expect to see happen on the graph, at least from an acceleration standpoint? Well, when the driver begins to move, we'd probably see an initial spike in acceleration, but then very quickly, as the driver begins to move sinusoidally, we would see the acceleration start to follow this graph instead, and pick up right at this spot in the graph. So if we sort of force that transition to happen here, we would see something like this. Kind of strange, but hey, that's just how the math works out. So let's revisit what actually happens when we take a reading with our oscilloscope. Here's the laser measurement of a sine wave that begins to play through the speaker. And now, here's with the mic signal. Here's the same test, but at a different frequency. So we can see the initial spike in the microphone signal as the driver begins to move outward. But the mic signal quickly switches to reading 180 degrees out of phase with the movement of the driver. So the microphone seems to be reading the acceleration of the driver, not the mere displacement or even the velocity of the driver. I should probably make an entire video on this topic, but the short and insanely oversimplified explanation here is that if the driver was moving outward and it slows down, that means it is going to be making a negative pressure differential in the environment as the air, which was kind of sloshing along with it like an ocean tide, has to adjust to the newly created void in the wake of the driver's sudden deceleration. That negative pressure is going to travel out like a wave effect at the speed of sound and pull the mic diaphragm outward just a little bit, and that movement outward will produce a negative voltage output. So when the speaker driver is in its maximum deceleration, which is way out here in the positive excursion region when it is slowing down and then changing directions to move backwards, the mic diaphragm is being exposed to the maximum negative pressure differential. When the driver is moving backwards through the midpoint of its travel, the overall pressure in the environment has once again stabilized because the air is moving like a block or a wind, because the driver is moving at a more or less set velocity at this point, which isn't very fast at all, maybe 10 or 20 miles per hour maximum, and the air can act quickly enough to create a new pressure equilibrium, even as it sloshes along with the driver like an ocean tide. The diaphragm would have to be moving a lot faster for this wind generation to become a sonic disturbance to the microphone. Winds can have the same internal pressure as the still-standing ambient air around them. So a wind itself won't really make the mic diaphragm move in or out like an actual pressure differential does. When the driver starts to slow down and change direction in the negative excursion region, the moving air sort of bumps into the driver as it unexpectedly slows down. The greatest positive pressure differential created in the air is going to be when the driver is way back here, changing direction most quickly, which is right as it is fully depressed and starting to move back out again. This positive air pressure wave will go out at the speed of sound and push in on the mic diaphragm and create a positive voltage output. So this is why microphones produce a reading for sinusoidal audio content that is 180 degrees out of phase with the actual motion of the driver in these free air conditions, even though when you run tests which involve non-sinusoidal content like pops or bursts, the mic reading will appear to be in phase with the driver. This is what explains the initial in-phase peak when the driver starts to move but isn't moving sinusoidally yet. And then we see the flip to 180 degrees when the driver enters sinusoidal motion. Basically, when the driver is making sound as we know it, the mic capsule is moving the opposite direction as the driver at any point in time. That's really weird to think about. You should be aware that some test condenser mics actually reverse which pin is hot and cold, so the output will be reverse polarity, which interestingly actually makes the sinusoidal sound waves appear to be in phase with what the driver is actually doing from a physical motion standpoint. But it's really confusing when you're trying to do basic polarity tests during setup. So just be aware of that when you're selecting microphones and doing tests and stuff. Okay, so this video could have been a lot longer, but let's just summarize what we've discovered so far. Typical high-pass filters, including merely the fact that analog inputs and outputs often block DC signals, add positive phase shift to the signal. And going through enough of them can stack up to phase shifts that extend up even into the normal subwoofer frequency ranges. So watch out. I recommend going digital throughout your system as much as possible to keep your subwoofer range sounding as linear and as faithful as possible. Speakers have electrical frequency and phase shifts that might not show up in their acoustic frequency and phase performance depending on certain teal small parameters, like when we saw the impedance spikes and the phase shifts in the current reading, even though the driver had a really smooth and consistent physical movement and acoustic response throughout those frequency ranges. Phase shift to the right on the oscilloscope corresponds with negative or downward shift on the FFT graph, which corresponds with both lateness in arrival time or a delay in the wave formation. As I mentioned in my other video on the topic, we need to know more about the situation itself and what we're actually measuring before we can know what's what here, because the phase graph alone won't really tell us this. The speaker driver in free air gets gradually behind the electrical signal as frequency increases and sort of caps out at around negative 180 degrees of shift. Sinusoidal sound waves will actually have a positive 180 degree phase shift in relation to the motion of the driver itself, at least in free air tests, and presumably under conditions where the driver alone is the main acoustic source. Test condenser mics, and perhaps most condenser mics, will output this phenomenon faithfully, although they probably have their own high-pass filter, which adds low-frequency phase shift. And some are polarity inverted, which will actually make the FFT reading more closely align with something like a laser measurement for sinusoidal content. All of this matters because let's say you're just looking at the main output of your mixer and you're comparing it against what your mic is reading from the speaker system. Well, you have several steps in between those 2 points, and each step and each element could be introducing all sorts of drastic frequency responses and phase shifts. And we haven't even talked about speakers that are in enclosures and what the venue itself might be doing to the sound, and what system EQ and dynamics and protection processing will be affecting. It could be very difficult to get to the bottom of what the phase response of your system is if you aren't meticulously accounting for each of these things. All right, well, thanks for watching, and I want to thank Filippo Bartolozzi specifically in the R&D department at B&C Speakers. He spent a lot of time with me helping me understand these concepts, and I want to thank the team at Nexo as well. They spent some time with me, and if you want to see other similar content, check out our YouTube page and just follow us on social media.